Hi everyone. Right now we're going to set up the coupled oscillator lab so we can get some data that you can analyze. You'll see here that we have two rotation sensors which are hooked up through a lab mini interface with a computer. And the first thing we're going to do is to couple the two pendula to the rotation sensors. So let me just do that and we'll be right back. Okay, and here's the second one. They just couple to the sensor with a screw through the pivot point here, like so. Make sure those are tight. Now you can see if we start one of these moving, the pendulum just swings. I'm not sure if you can just see the display of the computer, which is monitoring the angle as well. On the computer, we've just set up two displays in Logger Pro. The first is going to display the angle versus time for each of the two pendulum. The second one's kind of interesting. It's a Fourier transform plot, so it's going to show us the amplitude versus frequency for the two pendulum. And that's going to be important for this experiment. Finally, we just have to complete the setup. We'll go to Experiment and Set Up Sensors, select the LabQuest Mini, and then here we set it up to use the two rotation sensors that we're talking about. Second, we need to set up the acquisition so that we'll get the kind of data that we want. So now, going to data collection, we're going to take samples at the rate of 20 samples per second. That should be plenty. And then importantly, we're going to make the duration of the experiment quite long, 250 seconds. The reason for that is that when we go to measure frequencies using Fourier transforms, the resolution of the frequency graph is 1 over the duration. So if we have a duration of 250 seconds, then we'll have a resolution of, what is it? I think 0.04 hertz. And that's what we need for this type of experiment. One more thing, and then we'll get this set up and start taking our first measurement. Okay, our first measurement is just a measurement of the pendula, and I've started them, but they're not coupled to each other at all. Instead, we're just going to take data as they move freely. So let's start the experiment here. And off it goes. Here I'm going to auto scale so you can see the data as they come in a little more clearly. There we are. I'm not sure if the screen shows up very clearly at all. In any event, now we'll let this run for 250 seconds and see what we've got. We're taking data now. It's been about 60 seconds. Do you notice? Well, you can see the data versus time here, but do you notice in the amplitude versus frequency plot that we have a single peak? And you may notice that as the data continues to be collected, that peak is getting narrower and narrower. That's because as we get more and more data, we can more precisely resolve the frequency of the oscillating pendulum. It's kind of cool to see that in real time. Okay? And you might not be able to see, I've blown up this scale so that the minimum frequency is 0.5 hertz and the maximum is 0.8. So we're really zoomed in pretty far already. Okay, the data acquisition is all done now for this experiment. And you can see now how narrow the frequency, the peak here is, amplitude versus frequency after 250 seconds. So the frequency is very, very well resolved. I've zoomed out here so you can see how the amplitude as a function of time behaves. And the swings are so rapid you can't really resolve them. But you can see the amplitude slowly decay over that 250 seconds due to friction. All right, now I'm also going to take a screenshot of this so you'll have something to look at yourself. And we'll include the data as well in the packet. Okay,